Hello again. Today we're going to look at section 3.6 out of the book, which is sensitivity analysis. So this is looking at what happens when you start changing things in the model. We're going to take a first look at it today. We will be looking at it again in terms of some other concepts later on. Let's take this problem, a car manufacturer, problem we've seen in an earlier lecture. So we have two cars and we have two operations. Each car requires a certain amount of assembly and finishing and delivers a certain profit. Okay, so this is a problem we've seen before. We want to maximize profits. Here was the drawing of what we had. The graphical representation. We had the two lines that we had to be less than or equal to, and two lines that were greater than or equal to. So our feasible region was this four-sided thing. And when we saw it, we had this line, which was the various values of our profit. And we saw that if we kind of slide this line upwards, the profit increases, and we keep sliding the line until we are about to leave the feasible region. And where we're about to leave, that's where our maximum occurs. In this case, the maximum occurs right there at the point 3100, where we have $42,000 in profit. So the best route is to make 30 copies of car 1 and make 100 of car 2. Now, we're going to say what happens if we start to change some of these numbers. First, let's simplify it a little bit and say, okay, what about the right-hand side of the constant? Look at the constraints, the numbers on the right-hand side of the constraint line, the things that are holding us back. So we had this. We had 6x1 plus 3x2 is less than or equal to 480. I think that's the second constraint. And we're saying, okay, well, what if we suddenly, instead of having 480 hours available, we get 600 hours? What does that do? Well, remember, this is a line that is defining our feasible region. So our feasible region goes from being the original feasible region to an expanded feasible region. In our original problem, notice that those lines are still parallel. So the line of our original constraint and the line representing the new constraint are parallel. So if we don't move it too much, what happens? Our objective line still goes to the same corner, just kind of moved over a little bit. It's still going to be the intersection of our new constraint line with this second constraint line. It's going to be the same intersection so long as we don't move it too far. So we had our old maximum here. The orange line here is the objective function. We're going to find that our new maximum is over here. It's increased from 42,000 to 48,000, but it's still the intersection of the two lines. And it's the intersection of those two lines, just so long as you don't go too far. We'll get into that in a minute. But what does this mean? When we increased that size of the feasible region by moving our line, our constraint line, or the other way around, you could be decreasing the size of your feasible region if you had moved in the other way, if you suddenly had less hours. What happened? We said that we're changing from 480 to 600 hours. So we've suddenly got 120 more hours. New person working. Give me 120 hours extra. So when we did this, we saw that the objective function value changed from $42,000 that we had originally. Now it's up to $48,000. So our profit has gone up by $6,000. So think about the relation here. We are able to make an extra $6,000 with 120 hours of extra resource. Well, this is giving us a lot of information. This says that every additional hour that we have, everything is linear here, so we can just keep the relationships linear. This says that every additional hour that we have available is going to give us, well, $6,000 is what we make for 120 hours of extra time. That works out to $50 an hour. So this is giving us a very valuable piece of information for real-world problems. It is saying that adding extra time to the finishing process here is worth $50 per hour. So if I can hire somebody to add those extra 120 hours at $30 an hour, it's worth it. I'm going to increase my profits. However, if it's going to cost me $75 an hour, well, those extra hours are only worth $50 in profit, so it's not worth it. So this tells me how valuable that resource is. That resource, my second resource of finishing time, is worth $50 an hour to me at my optimum. That is called the unit worth of a resource, or it's also called a couple of other terms, the dual price or the shadow price. We're going to see in a later chapter why it's called a dual price. It's going to involve the duals of functions. Okay. But this sensitivity analysis tells me what my resource is worth. But there's a feasibility range. We can't extend it forever and keep making more and more money, because eventually that's not going to be the thing holding us back. Some of the other constraints are going to be holding us back. So if we picture this graphically, think of what's happening. We have our original line. We're saying that we can increase the amount available, the amount of time available under that constraint. We can increase it and make $50 an hour. But we can't increase it forever. We can increase it only to the point where the intersection of lines changes. If we increase it past the right-hand green line on here, that means that suddenly that's not our constraint anymore. That's not holding us back. Other things are holding us back. We could keep pouring more and more money into it. It's not going to make a difference anymore. Other things are going to be holding us back. If we were to decrease it, same thing happens. We can only decrease it so far until it stops being a binding constraint and becomes a non-binding constraint. Suddenly the intersection is changing of the lines that are holding us back. So either it means that it's a non-binding constraint, so it isn't going to have any relevance anymore. If it goes to the right, you can see that different lines are going to be the intersection points. Or if it goes to the left, you can see what's important is no longer the intersection of my two slope lines. Suddenly, the intersection of my green line with my vertical line is going to be the thing that drives the problem. When that happens, the value is going to change again. Instead of being worth $50 an hour, it's going to be worth a different amount per hour, but it's going to change the problem. That $50 per hour, the value of your resource, which we called the dual price or the shadow price, that value is only works in something called the feasibility range. It says if we move our line too far to the right, suddenly things change. If we move it too far to the left, it changes things again. So how do we get that feasibility range? Well, in the two-dimensional case, you can do it by calculating out what the value of that line is at the extreme right point or at the extreme left point. So if I want my line to go through that intersection, I can calculate that my maximum capacity, instead of being 480, has to be 900. So if I can have up to 900 hours of finishing where every hour is worth $50 to me. Anything more than that, things change. Going the other way, I can again calculate where that intersection is, and it gives me 440. So if my finishing time reduces to 440 hours, it's still worth $50 an hour to me. If it reduces any farther, it's a different economy. It's different costs. It's going to be worth a different amount because we're going to be dealing with a different point of optimality. This range is called the feasibility range. So long as my finishing is within 440 hours or 900 hours, it's worth $50 an hour to me. Fortunately, we have a quick way of getting it if we're using the Excel solver. So when you set up your problem, remember we saw with the Excel solver in the lesson a little while back, we said, choose the report to answer. Well, now choose another report. Also shade in that you want the sensitivity report. And look at what happens. That was our second constraint that we're talking about changing. We figured out, just by working it out by hand, that every hour is worth $50 an hour. There is my 50. $50 an hour is what it's worth. What was it allowable to? Well, I had 480 hours to start with. 480 hours. That's my constraint. I said I could go down as far as 440 with things staying the same. So I could decrease my number by 40 and it stays the same. Or I said I could go up to 900 hours and the value of it is still the same. So in other words, I could increase by 420 hours and I still get the same value for that resource. The Excel solver gives you your feasibility range and the shadow price in the sensitivity report. You can also look at the first constraint, which was, I think, the assembly. It says that it is worth $25 an hour. So if adding more time costs you $30 an hour, it's not worth it. But if it only costs you $20 an hour to add more people on, it's worth it. It said we had 720 hours to start with. We could increase that as far as 800 hours before the equations change. We could decrease it by 280 hours before the equations change. So long as we're within that range, within that feasible region, things stay the same. What about the last two constraints? Those are non-binding constraints. So around our point of optimality, it doesn't matter what we do with them. They can change, they can go up, they can go down. It's not going to impact my point, my optimal point. And again, we have increases and decreases. So we can increase our third constraint by 10 without it having a difference. We can increase our second constraint by 70 before it makes a difference. So again, even when the shadow price is 0, which it is for non-binding constraints, we have a feasibility range. And in this case, we are allowed to decrease. Excel uses this 1 times 10 to the 30th, which means infinitely far. So we can decrease it as far as we want to with no impact, and it doesn't change the optimum point, but we can only increase it so far. So that's the idea of a dual price or a shadow price. It's the value of your resource. Okay, so that's looking at the right-hand side of our constraints. Let's jump up to our objective. So again, here's the same problem. I've taken out a lot of the clutter, so we're just looking at the objective function. What happens if we start to change the coefficients in our objective function? How does this change our optimum value? Well, when you change those numbers, what you're doing is you're changing the slope of your line. So you're pivoting your line to one direction or the other. And you can see by looking at this in 2 dimensions, that so long as you pivot it and it doesn't go past parallel with one of your binding constraints, then the point where the optimum value occurs doesn't change. So what this means is changing small changes to your objective coefficients doesn't change the value of your optimum value. But again, what do I mean by small changes? How can we figure out small changes? Well, it's using the idea that you don't want to pivot your line past where it's parallel with a binding constraint. And again, the Excel solver gives us those values. So if I read this, this is saying my original optimum function was 400x1 plus 300x2. What if I change x1, the profit of my first car? What if market conditions change and suddenly I'm making more of a profit? Well, it can go up $200 per car without changing the objective function, the value of the objective function. So if the profit goes up to $600, my linear program still tells me to make 30 cars of one and 100 cars of a second. If it goes up past that, if it goes up to 650, things change. And suddenly, to maximize my profits, I have to have a different mixture of cars. It also says that I can drop that by 200. So if the profit of car 1 goes as low as $200, $400 minus 200, if it goes as low as $200, I don't change the mixture of cars. If suddenly the profit drops to $180, I need to relook at my mixture of cars. Again, for the second type of car, it says, oh, sorry, I was thinking 400. Yeah. It says that I can have 300, my profit is $300 per car. I'm allowed to increase that up as far as $600 without making a change. I'm allowed to drop it to $200 per car before I have to make a change. That is called the optimality range for the coefficients. Just a note that the textbook defines it slightly different. I'm not a fan of the way the textbook defines it because it defines it for only two-dimensional variables. I like to use a definition where it talks about the optimality range for a given variable, because then it makes sense in multiple dimensions. So this idea of the optimality range, the shadow price or the dual price, and the feasibility range for the dual price can be read off of the sensitivity report in Excel. But now we're going to put Excel aside and say, okay, let's take a look at our simplex tableau and see where are these numbers coming from, because we want to understand how these numbers are being generated. In 2 dimensions, I could show you a picture to show how it works. In higher dimensions, it's a lot harder. So let's go to the tableau and see where these numbers are coming from. First off, the first thing we did was we asked what happens if we change the constraints on the right-hand side. So we're going to rewrite, this is the same problem, but we're going to rewrite our right-hand side constraints with a variable in there. We're going to say, okay, if we increase, oh sorry, this is a different, slightly different numbers. So if we increase our right-hand side so that we're dealing with 30, so that instead of having our first constraint less than or equal to 32 is less than or equal, we change the 32. And we're going to say, we're going to use a variable to say how much that changes. So D1 means how much we're changing it. So our first constraint says we have 32 and we're increasing it by D1. Well, we can rewrite our tableau a little bit in this way. We can add extra columns for the D's. D1, D2, and D3 to keep track of what kind of an impact they're going to have. Now, here's a very important thing to note. Take a look at your values of D1 to start with, and take a look at your S's. They're the same. This represents the solution or the feasible point that you're at right now. So the feasible point we're at right now gives us the first equation gives us 32 plus D1. The second equation gives us, or the second constraint gives us 40 plus D2, and the third one gives us 30 plus D3. So this is representing our equations in an expanded tableau. But because the slack variables and the change variables, the difference variables, have the same numbers, that makes our life a lot easier. So now we've seen this problem before in one of the earlier classes. So we saw that the first step is to choose -5. It gives the 4 in here as the pivot entry, and the leaving variable is S3. So after you do the first pivot, you end up with this. This is when you just use the rules for the simplex method. Note again, after you do it, your S's and your D's, your slack variables and your difference variables have the exact same values. So as you go through this simplex tableau, those columns are going to be the exact same at every step of the way. We can run another tableau on here, another iteration. We pivot around x1, we take s2, and after our second iteration, which this is a problem that we saw last class, we end up with our optimal tableau, which says the optimum value is 40, and we have basic variables of S1, X1, and X2. So this is our tableau, our terminal tableau, where we have our optimum solution. Again, here's the optimum solution. Let's just copy the same tableau. This block on the right-hand side, that is our solution. So now let's take this and just write out what this means. So Z, again, we ignore all the stuff in here. Normally in our tableau, it would tell us that Z equals 40, S1 equals 2, X1 equals 5, and S2 equals 5. But now we have this extra stuff because we introduced these D's on the right-hand side. So if we write this out, just using that first line, we have Z equals 40 plus 0D1 plus 0.25D2 plus D3. That's our first equation. Our second equation, S2, is 2 plus 1D1 minus 1.5D2 plus D3. And there's our second equation. And so on for the third and the fourth. So we can read off what is on the right-hand side of our equations after 2 iterations. And remember, the tableau is just substituting variables in our equations. So the tableau is telling us what our equations look like once we're done and we set some of our variables to 0. So now, what does this tell us? Well, we have these equations. First off, take the Z1. The Z1, our optimum equation, our objective equation, after it's been rewritten after 2 tableaus, after 2 iterations of the tableau. What does this tell us? Well, this tells us, remember, what we're looking at is As we increase our availability of a resource, in other words, as D1, D2, or D3 go up, how does that change the value of our objective function? Well, this tells us right away D1 is not in there, so if we change D1, it's not going to impact our Z. It's not going to impact the value of our objective function. What about D2? Well, there's a 0.25 D2, so that tells me that every time D2 increases by 1 unit, the value of my objective function goes up by 0.25. There's my second point. As my second constraint changes, the objective function changes by 0.25. I have 1 D3, so that tells me if I increase D3 by 1 unit, my Z increases by 1 unit. That's my shadow prices. My shadow price for D1 is 0. My shadow price for D2 is 0.25. My shadow price for D3 is 1. Here is the Excel output from the solver, and you can see those numbers right there. The shadow prices or the dual prices. What is that resource worth? The first resource is non-binding, so it doesn't matter. I can change it. It's not worth anything. My second one is a binding constraint. It's worth, a change in that constraint is worth 0.25. My third one is a binding constraint. One change of 1 unit there is worth 1 unit on my Z, on my objective function. That's my shadow prices. And I can see where they come from by rewriting my original equation with the plus D1, plus D2, and plus D3, seeing what happens after each iteration. And then from the tableau, I can read off my solution, which gives me my shadow prices, which gives me the value of that resource. What about this feasibility range? Remember, I said the feasibility range is, well, we can't change the resources forever. There's this range in which I can change the resource and still have the same value of it. So my resource was worth $50 so long as I didn't change it too much, change my problem too much. Well, how do I get that? For this, look at those constraints that we rewrote. When we'd finished our tableau, remember we rewrote the objective function and we rewrote the 3 constraints. Here are the 3 constraints. But remember, one of the things we have to do is all of our constraints, all of our variables have to be positive. So that number on the right-hand side represented the value of S1, the value of X1, and the value of X2 at your optimum point. Those have to be positive. Well, when I read it off, I got that S1 was equal to 2 plus D1 minus 1.5 D2 plus D3. That whole thing has to stay positive. So 2 plus D1 minus 1.5 D2 plus D3 has to stay positive. This is giving me my feasibility range. If I set D1, D2, and D3, in other words, my differences in my constraints, if I change those, this equation had better not go negative. Otherwise, I've changed my problem and my point of optimality has changed. So figuring out the feasible region means figuring out where my variables remain positive. Now, with a lot of variables, this can get complicated, but what we can do to figure it out is figure out the optimality range or the feasible range for a given variable. So we can just take D1. Now we can ask the question, well, what can I change D1 to if I don't change any of the others? and still keep that same uh, dual value or shadow value? Well, if I look at my equations, D1, I can say set D2 and D3 equal to 0. So in other words, I'm not changing my constraint on the second and third equation. I'm only going to change the constraint on my first equation, which is D1. So D1 is going to become non-negative. It could go up or it could go down. It could be positive or negative. What do these equations tell us? Well, these equations, D1 is only in the first equation. The first equation tells us that if D1 is greater than or equal to -2, I'm okay. So that is my feasibility region. My feasibility region is D1 is given by D1. The difference can go down as far as 2, but it can go up forever. And it's not going to change my point of optimality. What about my second one? Well, if I want to figure out the feasibility region for my second variable, I have to say, okay, I'm not going to change my first or third variables, so those are equal to 0. The differences are equal to 0. But now let's see what kind of adjustment I can make my second one and still keep my variables positive. Well, that tells me, the first equation tells me it has to be less than or equal to 4/3, it has to be greater than or equal to -10, and it has to be greater than or equal to -20. One of those things is redundant in this case, so my D2 has to be between -10 and 4/3. So I can drop my second constraint by 10 units, or I can increase it by 4/3 unit, and I don't change the value of the shadow value does not change. My third one, this should be D1 or D2 equals 0 because I'm changing D3. You go through the equations again, and I get my feasibility range for D3. So the simplex method with the tableau gives us a conceptual idea of how the feasibility ranges are being calculated, and it all comes down to the fact that my variables all have to be positive or non-negative. If they drop into the negative, what I'm doing is I'm changing my problem. And that changes the value for my dual value or my shadow value. And you can see that on the Excel output. This is what we calculated for this problem. That was our feasibility ranges. If you look on the Excel output, those are the exact same numbers that you see. The increase that you're allowed or the decrease that you're allowed. So for my first constraint, my increase is infinite. My decrease is 2, which means my difference has to be can be no more than -2. Can't be any smaller than -2. If I drop it any more than 2, I'm changing my problem. So again, the Excel output gives us those ranges. And you can see how the tableau gives us the exact same numbers. Okay, let's jump up to the objective function. So we saw in 2 dimensions what happens when we start to change the coefficients on our objective function. So here is a problem looking at a coffee mixture that wants to maximize profits. There are certain amounts of beans in each. We have to combine the beans and we get certain amounts of profit with the different products. So go through this, make sure you know you're comfortable with changing this word problem into a linear program. We end up with this linear program. This is a straightforward linear program again. We can solve it with Excel, or we can look at it through a tableau, which is what we're going to do to see how we can get a feel for changing the coefficients in our objective function. So we're going to ask what happens if we start to change our coefficients in the objective function. And how does it impact our tableau? Well, if we just take our original problem, what do we get? We have this is our initial tableau. One iteration gives us that. Or sorry, a couple of iterations give us that. That was our terminal tableau, our final tableau, which I've repeated here. Our final tableau gives us the reduced cost right away. So, or something called the reduced cost. On our final tableau, once we've gotten our final value, take a look at what it says here. It says that our basic variables are well, actually it has a slight misprint here. Our basic variables should be x1, x2, and s2. Our basic variables there. So if we read off the value of our objective function from the top row, we get this. We now have a maximization of minus 5x3 plus 1.5s1 plus 0.5s3. Notice this has two slack variables, and it has one of our original variables. Well, this number here, this 5, what does this tell us? This tells us that if we increase x3, so that third blend of coffee, every unit of that blend of coffee that we increase by in our production drives down our profit by $5. That is called the reduced cost. So increasing the production of something reduces your profit. It's called the reduced cost. And in this case, the reduced cost of our first blend is 0, of our second blend is 0, but of our third blend is 5. What is this meaning? Well, if we take a look at our Excel output again, you can see the reduced cost is one of our columns. So it says that if you increase x3, your profit goes down by 5. And you can see that reflected in the final value. The final value says we don't produce any of x3 because it costs more for us to make it than we get in profit. Well, where does this come from? If you remember the x3, this was the statement from our problem. It said that mixture C required 4 pounds of mild coffee beans, 5 pounds of medium coffee beans, and produces $1 profit. Take a look at the shadow values, the shadow costs for this. 4 pounds of mild. So the cost of producing this, it takes 4 pounds of mild times what? What's the value of the resource of mild coffee? That's the shadow value. The mild, that was our first one. The shadow price was 1.5. The cost of producing that also costs 5 pounds, or it requires 5 pounds of our medium blend coffee beans. Well, what is medium coffee bean worth? What's the shadow value of medium blend coffee bean? That was our second constraint. Our shadow price was 0. So our cost is 4 times 1.5, which is 6. Increasing. So every unit of increase there's a penalty of $6 that you pay. What is the profit? Well, our problem says that every unit of this produces a profit of $1. So increasing the production has a $6 penalty, but only $1 profit. So the reduced cost is $1 profit minus $6 penalty, which is -5, which is exactly our reduced cost. Because remember, if we produce this, it means we have to produce less of something else. So the cost to our entire system means that we have $6 in penalty, we have $1 in profit. That means we have $5 of loss. Every unit you produce of this means $5 loss profit. That's the idea of reduced cost. And this is how we can read it from our tableau. Now, what about these optimality ranges? We said that the optimality range is how much we can adjust our the slope of our line and not change our point of origin or our point of optimum. Well, if we look at our original one, we're going to do the same thing. This was our original optimum function. We're going to say, well, let's change the value of our coefficients by a certain amount. So this is the same trick that we did earlier. We're going to add a value to our coefficients and see what happens. But what happens when we throw those in the tableau? That changes our starting tableau by changing our numbers up above. We can still follow through with this. We can still continue with the tableau the same way, using the same rules or a very slight modification of the rules, and come out with a final tableau that looks like this. So what does this tell us now? Well, remember what had to happen for a terminal tableau. We were finished our iterations when all of the numbers across the top are positive. So we're saying we can adjust these things and not change our tableau. Well, that better mean that all of our numbers on that top row have to stay positive. Because if one of them goes negative, we have to do another iteration. So this has to be positive, this has to be positive, and this has to be positive. This is giving us a range for our D's, D1, D2, and D3, that we can't violate without having to iterate again. So let's pull those out. Here are the three equations on the top row after we've done our iterations. We do the same thing we did before. We're going to say, well, what if I only change D1? In other words, if D2 and D3 stay 0. Well, these equations give us conditions. So it gives us conditions for D1, and it says that D1 has to be between -5/3 and 2. What if we change D2? There's our optimum range for D2. What if we change D3? There's our optimum range for D3. So this is telling us how much we can change the numbers, the coefficients in my objective function and still keep the same point of optimality. If I violate these numbers, for instance, if my D2 goes up by 3, I have to recalculate because I've got a different point where my optimum occurs. And again, we can read these numbers off of the Excel output. Here were the conditions that we ended up with, that we calculated by hand. Take a look at our Excel output. You will find those exact same numbers right here. This represents our objective values. We have a reduced cost of one of them, of 5. And our objective coefficients, that's what we started with. And this says these give us the exact numbers that we calculated using the tableau for how much we can change one of these values before we have to recalculate. So it tells us that if my profit on my third item goes up by 10, I'm still okay. If it goes up by 11, I have to recalculate my optimum value. All right, that's an overview of sensitivity. That was a lot to take in. If you haven't done this before, and even if you have done this before, it can get confusing. Practice these. Try to get a feel for what these changes mean, what reduced cost means, what shadow values mean, what your feasible and optimal ranges are. Thinking about it in terms of 2 dimensions gives you a good feeling for them when you're dealing with larger dimensions. The concepts stay the same. It's saying how much can you change things before I have to recalculate my problem, and if I change things, how much is my objective value going to change? What is a resource worth? These are very important questions in reality when you're dealing with situations that can be solved by linear programming.